Okay, so let's just recap a little bit about what we were doing in this because it's been a little bit, we've had a little bit of a gap. So we were talking about electromagnetic waves, and this thing basically came about from looking at Maxwell's equations, and Maxwell was able to describe basically the nature of light and derived it from basically these fundamental laws of electromagnetism. So from looking at electric fields and magnetic fields, basically what he found was a solution where sort of like one field would actually kind of produce the other. And this was because there are these terms that are these time-dependent terms, and these changing electric field produces a magnetic field, and a changing magnetic field produces an electric field. So, you know, unlike the normal situation where there's a charge and then there's an electric field, or there's a current, there's a magnetic field, these are kind of produce each other. So it's kind of interesting that, you know, this can be possible even without any charges or currents, right? So this is why light seems to be very different, but actually has the same origin. So, you know, we're quite sort of familiar with electromagnetic waves these days, of course, because there's so many applications for them. So apart from the light that we can see with our eyes, there are many different other frequencies of electromagnetic waves. So pretty much, you know, the full electromagnetic spectrum is actually used in various types of technologies, ranging from radios to microwaves to X-rays, gamma rays, things like this. So how actually do you make these waves? Well, we saw a video over this where if you have charged particles and then you oscillate them, and well, you don't have to oscillate them. Actually, the main thing is to accelerate them, but oscillating them is a good way of accelerating them, because when you oscillate something, it's constantly changing velocity, right? And acceleration means that you change the velocity. So we saw that actually, if you oscillate actually a pair of charges like this, this actually produces electric fields such as to actually make this kind of wave type of pattern. And this wave type pattern, once you create that wave type pattern, it can actually propagate in space. So a typical way of doing this is through an antenna. This is basically what happens in an antenna. The charges, there are positive and negative charges which oscillate back and forth within the antenna, and this actually produces electromagnetic waves. The reverse process also happens, and so apart from transmitting them, you can also receive them with the same kind of thing. Okay, so you know, we talked a little bit about radios, how they work. Radios, of course, there's a radio station transmitter inside the antenna that's transmitting the waves. The charges are going up and down, and then receiving on the receiving end, also charges go up and down. And in order to amplify the signal, we were talking about these oscillators that are attached to the antenna. And so the analog of this for sound would be something like a guitar. It makes the sound much larger. So this would be like the transmitter, of course. So we talked about such oscillating circuits because we're talking about, you know, electrons, charges in metals moving around. This an oscillating circuit for that would be something like this, which is a combination of an inductor and a capacitor. So you combine these things, charges oscillate. Yeah, so we talked about capacitors and inductors, and we did a little demo like that, just breaking it down. And yeah, so basically how radio works is that, you know, you have this tank circuit or this LC circuit, which is both on the transmitting and receiving side. So if you actually look inside an old-fashioned radio, then you'll see one of these things is the inductor, and this thing here, which is attached to the tuning dial, is, you know, to change the station, is variable capacitor. So it's just the capacitor inside the LC circuit. It's just that you can vary it so that you can change the frequency. Yeah, I talked about polarization. And so this is why, when you have an old-fashioned radio, you want to rotate, you try and change the direction, and then, it picks up the sound better or worse because, the orientation of the antenna actually really makes a difference because there's polarization of the light. And yeah, there's various different frequencies like this. Already talked about it. And then the size of the actual waves determine also the size of the antenna. So, AM radio transmitters are pretty huge towers like this compared to mobile phones. Mobile phone transmitters, which are much more compact. But the trade-off is that the range is quite different. So, for AM radio, all we have to do is build one of these giant things, and then that will propagate to, very long distances. Whereas for mobile phones, you need to have lots of these things. So, if you want good mobile phone reception, okay, each one is smaller, but you need to build these all across the city. So, they need to be absolutely everywhere. And so, of course, we're kind of used to this idea, when we're walking around with our mobile phones, like reception goes sort of in and out, basically because, if we're out of range of one of these transmitters. Okay, so somewhere where we got up to, somewhere around here. So how do you actually encode, the information? And so, I'm sure you've heard of AM and FM radio. I mean, okay, so these days people don't even use that, use digital radio. But old-fashioned radios, you have the AM frequencies and then the FM frequencies. So just like what we have here, AM stands for amplitude modulation, and so basically the sound is actually encoded in the amplitude of this wave. So you have the basic wave, and then what we're basically modulating here is the amplitude of the wave. Whereas frequency modulation means you actually change the frequency. So the amplitude is actually fixed, but then the frequency is variable. So so this is how you sort of encode information into the wave, because basically you have the base frequency, but then by changing the frequency or the amplitude, you can basically encode some further information into it. So when you listen to AM or FM radio, what's really happening is that actually it's this kind of signal which is eventually arriving at the radio. But I mean, what's actually much more relevant these days is digital encoding. And I mean, digital encoding basically still works in the same way. It's just that instead of actually having the signal as being like, say, the amplitude or the frequency, and that would be like a continuous quantity, you instead actually just digitize everything, so that when you have the frequency which is arriving, you have again the base frequency, and then so you can do this with a sort of an FM or AM kind of style, or actually even this phase kind of method. But the difference is that basically you have the base kind of wave, and then you're going to change something about it, and then basically whether it's a 0 or a 1 in the digital encoding is going to be encoded by, for example, maybe like a large amplitude versus a small amplitude. So 1 and 0 like this, or in the FM kind of style where you have like slightly high frequency versus low frequency. And so on the receiving end, you can retrieve the digital information by looking at basically either the amplitude or the frequency, or actually there's another way to do it, which is using the phase of the light. So basically you can see here that here the phase basically means like where which cycle of the wave that you're actually in, right? So you can see here that for the one encoding, basically, if you look here, this is the block for the one. For all the ones, basically the say this initial point here, the wave actually initially goes up here, right? And then so it initially goes up and then down, up, down, up, down, up, down. Now for the zero part, actually initially the wave actually goes down. So actually, if you synced these things up, then what you'd find is that this first part of it, the wave would be like positive, whereas in the first part of it, the wave would be negative. So you kind of compare the timing of the phase, which is whether it's initially going up or initially going down, and then that is going to encode your 0 or 1. And basically, any kind of digital transmission, there's various uses of these things, but it eventually is encoded and decoded in this way. Okay, so often you hear about when you're talking about your internet connection and things like that, you have like a high bandwidth or a low bandwidth. You might have wondered, obviously high bandwidth kind of means like, a lot of information can be transferred. So if you've got like a sort of high bandwidth connection, then that means that you can transfer, like say, your internet extremely fast. But you might wonder, what actually is this bandwidth? What bandwidth are we, actually talking about? So basically, where this word comes from is, so when you have like particular parts of the electromagnetic spectrum, then what you generally do is to sort of chop it into different frequency ranges. So, easiest one to understand is things like radio. So, when you have a radio, then of course you tune it to some frequency, right? So if you're listening to AM radio, then each station has a particular frequency, right? So often the frequency for AM radio is something like this. So when you adjust the tuning dial on your radio, then you are basically changing the station frequency somewhere in this range, like 540 to 1600 kilohertz. Now, of course, it doesn't mean that you tune it to that station and then it's only that frequency that's actually coming from the radio station. There's a bit of variation, and you need that variation because otherwise you wouldn't be able to you're listening to the station to listen to some music. You're not listening to the station just to hear like one tone, otherwise the radio station would not be able to play any kind of music, right? So each radio station has some frequency range. So say like the radio station is at, the tuning is at say 1000 kilohertz. Okay, so that's your tuning on your dial. So in actual fact, it's going 1000 kilohertz, but plus or minus 5 kilohertz either way. So the actual frequencies that it's transmitting is somewhere between 995 kilohertz and 1005 kilohertz. And then so using that range, you actually encode the music. Well, not really encoding, but you're basically putting the music that you're trying to listen to on top of that particular range. So it's 1000 kilohertz, that's sort of the middle frequency, but it's going 995 to 1005. So does anybody know what the range of like the human ear is? Like what frequencies can we hear with our ear?
Is it like 20 to 10,000? I'm not sure.
Yeah, I think you're remembering correctly. So yeah, human ear can, yes, hear, like the lowest frequency you can hear is about 20 hertz. And then the highest frequency, like, and actually probably most people can't even hear it, is about 20,000 hertz. Yeah. So of course, with age, your hearing deteriorates, but that's the maximum range probably that a human can hear. So I mean, 20,000 hertz is super high frequency, but around 10,000 hertz is like pretty regular, just a high pitched sound. Yeah. So if you listen to a piece of music, there would be definitely some frequencies in the range of like 10,000 hertz, maybe 15,000 hertz, definitely, right? And then super low basses would be somewhere 100 hertz or maybe less. So when you listen to AM radio, basically it has a range of only plus or minus 5 kilohertz. Okay, so that means that the highest sound that actually you can actually conceivably transmit on AM radio is only about 10,000 kilohertz, and that's like way below kind of the range of human hearing. So you guys would definitely, you guys are still all young, so you could probably hear up to 17,000, 18,000 kilohertz, no problem. So 10,000 kilohertz is actually like pretty low frequency. It's pretty muffled actually. If you cut out all the frequency in a piece of music above 10K, then it'll sound like it's well, coming out of an old radio, basically because that's exactly that's what AM radio is. It's very actually limited in frequency. You only can go up to about 10,000 kilohertz, the maximum frequency. So this actually explains why AM radio actually sounds pretty bad, right? So if you ever listen to AM radio, generally, AM radio is used for just people talking, or maybe some very old-fashioned music and stuff like that, where people are kind of used to not having that really high fidelity sound. So that's AM radio. FM radio has a much larger bandwidth for each station. So if you're familiar with FM radio frequencies, it goes from something like 88.1 to 108.1, and then each notch, each station, when you change it, it goes up by about 0.1 megahertz. And so that is actually plus or minus 100 kilohertz frequency. And then so if you compare that with human hearing, that's like way higher. Okay, so the best people could only hear 20 kilohertz, and this is like plus or minus 100. So that's there's a lot more frequency range that is actually allocated to the FM side than the AM side. So this is why FM radio actually sounds much better, because they can encode much higher frequency. Now, of course, for digital radio, because it's not directly actually encoded in the wave, it doesn't really actually matter. All that really matters is like how much data that has actually happened, because of course, in digital radio, you chop up all the information of the music or whatever it is that you're receiving, and then all that data is actually used to reconstruct the piece of music. So it's not like a direct mapping of the music onto the wave. It's just a matter of how much data that you can send. So in this case, do I have a slide? No, I don't have a slide here, but in terms of when you say a high bandwidth kind of say connection, basically what is happening there is that actually you are sending lots and lots of information in different frequency ranges, and so for each frequency range you'd be able to send some amount of information. There'll be a information transfer rate, and then the larger the more bands that you use of the frequency, of course each channel can transmit that amount of information. And so if you add up all that, a large bandwidth basically means that you can transmit, a lot of information. So generally speaking, basically in all these things, either AM, FM, or digital, you can actually, you obviously transmit much more information if you're using much more of the electromagnetic spectrum sort of bandwidth. So bandwidth just basically means like how much of the frequency range of the electromagnetic spectrum you're actually using. The more bandwidth that you're actually using, the more information that you can send. And so this is basically why we say high bandwidth. I mean, people consider it synonymous with just large amounts of information, but this is where it originally comes from. Okay, so in terms of understanding how mobile phones work, I think there's a nice video here which just sort of explains this. So let's just have a quick look at this video.
Part of our lives. Let's try to transfer 0.
So yeah, I think that's most of basically what I think this video saying in terms of the physics. But yeah, so it's kind of interesting to see that well, this is how mobile phones work. I mean, in the first part of it, basically, this is exactly the kind of stuff that we were talking about. But the thing with mobile phones is that basically, actually, you're actually communicating using, just basically the same kind of idea as, radios. In fact, it's just that the frequency range is a bit different, and also you're of course using digital technology. So, encoding the information digitally, and finally, basically, mobile phones eventually work not by directly transmitting the actual wave from, of course, the sender to the receiver, but just to your nearest base station, and then it connects by optical fiber the rest of it. Okay, so let's just, yeah, okay, so basically, yeah, so the key points there are that, yes, because, there's so many different people using the mobile phones, obviously you couldn't have a different frequency range. So this would be the equivalent of having, a different radio station frequency for each and every person. So obviously there are basically way too many people all trying to communicate. So basically there has to be kind of a smart way of reusing this frequency range. And so, all these things are kind of dynamically done. So that, within some, physical geographic region, these kind of frequency range are all assigned to people dynamically. Okay, and so saw a little bit about, differences between these, 4G, well, all the way from 1G to 5G. Okay, so I hope that gives you a little bit of an idea of how basically, mobile phones work. I mean, basically, in the end, it is actually fundamentally, not really so different to just regular radios. I mean, the only difference is really that, well, certainly the encoding is digital, and then the frequencies are kind of different. But I mean, fundamentally, it's really still the same kind of idea. You're using electromagnetic waves to encode some information. Okay, so the encoding is digital, not analog, that kind of thing. And also, because of the sheer number of people that are actually trying to transmit. So, it's a bit like every mobile phone that you have is like a little radio station, if you like. So you have so many sources, so you basically have to get around the logistical issues of that. But basically, you know, at the fundamental level, it's actually no different. Okay. Any questions anybody had on this topic? Okay. No. All right. Then let's get on to sort of the next topic, which is talking about microwave ovens. So, you know, this is a kind of a pretty common kind of appliance. And of course, this is also based on electromagnetic radiation. But, you know, it doesn't sound very exciting, microwave ovens. You know, it just sounds like some, you know, something that you have in the kitchen. Obviously, no longer something that's extremely high tech. But nonetheless, they're pretty remarkable devices. And obviously they have quite a different way of working as opposed to conventional cooking, you know, say with a fire or something. So just directly heat up something. So, you know, some questions that we might explore in this section are things like, so why are microwave ovens so efficient? So obviously, you know, you can heat up something in a microwave, you know, much more quickly than with a conventional gas stove. So, you know, why is that the case? You know, you often see microwaves have these turntables. So what's the deal with those? Often you are, you know, you're told do not put metal in microwaves, right? But have any of you ever put metal in a microwave? Do you know what happens? Let's see, chat. No. Okay. All right. Okay. Thank you. Thank you for that. Yeah. Well, often, yeah. So I just as a sort of a little side story, you know, in preparation for these lectures, actually for this part of it, this is another demo that I was going to actually do in the course. I'm sorry you guys will miss out because you know, we can't all be together. And so one of the things that I prepared for this part of it, I actually bought a microwave oven. It's just sitting there in my office now. And basically, you know, we were going to microwave a bunch of stuff, particularly stuff that you're not allowed to microwave, right? And so just as a little test, I just put, you know, some piece of metal. Like I was going to put a fork inside a microwave, and I was just going to test it out with the microwaves that are just in the kitchens here. And then, you know, when I started to do this, just like my colleague, just absolutely freaked out because he thought that, you know, the whole thing's going to absolutely explode or something like that. People are very scared of actually putting metal in the microwave. Actually, it's not as dangerous as people actually think. So everybody's being educated so well that people actually don't dare to put anything like this in the microwave. You know, I must admit, I hadn't really put that much stuff, the metal in the microwave before, but you know, we can understand a little bit. Well, what we'll do here is to understand, like, basically why, you know, what actually happens and why is it considered dangerous. Some other questions are, so why do objects some remain cool in the microwave, some become hot, and why does ice not heat up very well in the microwave? So, you know, some of these questions we will, I think all of these questions we'll explore. Okay, so yeah, so apart from metal in the microwave, there are all kinds of other things which you're not supposed to put in the microwave, such as paper bags, takeout containers, yogurt butter containers, eggs. This is another one. Also grapes. Has anybody ever put grapes in a microwave?
Why would somebody put grapes in the microwave?
Sorry, you know somebody that's put grapes in the microwave. Do you know what happens?
No, I mean, why will people put grapes in the microwave?
Okay, why? Yeah, okay, I suppose so. Just for fun, I suppose. It's actually very interesting. You know, you wouldn't think it would do anything that special, but actually, if you put grapes in the microwave, actually, again, it's something quite violent. Violent happens. We'll look at that. Obviously, things with metal in that, you know, cookware with metal trim. So these are your, you know, grandmother's plates with maybe some metal on the rim of it, things like this. Yeah, this is stainless steel, frozen meat. This is actually eventually more of a health issue rather than a danger issue. Aluminium foil, that's another metal one, and so forth. So, you know, there's all these different types. So we'll maybe explore some of these. All right, so let's just start off with a little bit of background of, well, what we're talking about here. So microwaves are, well, they're just basically any other frequency of electromagnetic radiation, actually. And they're called microwaves because they're typically in the 1 millimeter to 1 meter range. So the wavelength would just be somewhere between 1 millimeter or one meter. And so because it, I guess, contains, well, sort of micro generally means something kind of small, but not extremely small. So this is sort of why it's called microwave, I guess. And if you're talking about microwave ovens, then this uses a very specific wavelength of 12.2 centimeters. So just, you know, around about the size of your hand. If you could see it, then the waves would be that big. Okay, and this just fits into a particular frequency range that is basically on the slightly lower frequency side of the infrared range. So, you know, it's the colors that we see with our eyes. They have wavelengths, you know, somewhere around about 500 nanometers. So that's extremely small wavelengths. And then infrared is a bit longer than that. And then there comes microwaves, but they're not as long as the radio waves, which we've already talked about. Okay, so why is it 12.2 centimeters? Well, hold on. Well, okay, I'll finish talking about this. So why is it 12.2 centimeters? Well, if you actually look at the frequency response of basically water. Okay, so if you look at the power that is going to be absorbed by water at various different frequencies, what you'll see is actually the relevant thing is actually the blue curves here. So don't worry about the red curves. This is basically what is actually going to be absorbed here. And depending on the temperature of the water, actually it will, the response, the absorption will actually shift. And for water that's like 0 degrees, the peak is more like, say 5 centimeters. This is the wavelength that is best absorbed by water. As you go to hotter water, so like boiling water, then the wavelength that's best absorbed is actually more like, 0.5 centimeters, so about 5 millimeters. Okay, so actually the temperature of the water actually will affect which frequencies are best absorbed. Now, I said it was 12.2 centimeters. So actually that's around here. So actually looks like this is not really the optimal temperature. If you were to just look at these graphs, you would think that the best frequency that you should use, because basically, you know, when you're cooking in a microwave, you're actually just heating up the water inside the food. Okay. So if you just looked at this, you would think, well, probably around, 1 centimeter would be a better wavelength to use because that would actually absorb the heat better. Does anybody have any idea why it's actually like 12.2 centimeters? No guesses? Okay, all right. Well, I suppose I wouldn't have known either. Okay, so the answer is actually that it's kind of a combination of how efficient it is in actually absorbing the water. So of course you want the water to absorb the power the best, but actually you also want to heat up the food in, kind of evenly, right? So what you don't want really is that, for example, the microwaves actually just heat up like the surface, and then inside of the food is completely cold, right? So actually, what happens, like say if you use a wavelength of say 1 centimeter, say this looks like something which is a little bit like more in the range of like where the water actually absorbs the heat. What you actually find is that it's kind of like the water is kind of not transparent enough. So for our visible light range, so for the light that we see with our eyes, water is quite transparent, right? So light actually goes through it no problem. So this is actually like the absorption coefficient of light. The light range within this dotted range is actually this is the frequency of the light that we see. So actually, what you notice if you look at this graph here is that water is really actually not very transparent at almost all frequencies. So it's kind of lucky that there is this kind of frequency range that water is somehow transparent to. If our eyes were able to detect other frequencies, then probably what we would kind of think of water is not like this kind of clear liquid, but actually this completely opaque liquid that you can't basically see through. So, for example, if our eyes were much more sensitive, say to the microwave range, you would jump into a swimming pool, and then immediately it would be completely dark, right? So basically, you jump in, and then it's completely going to be dark after just a very very small depth, right? So maybe like already after 1 centimeter, it'd be pitch black. Whereas in our visible light range, we can actually see through the water quite well. In fact, you might say that this is not really an accident. Our eyes kind of evolved with this because actually it was much more advantageous to be able to actually see in water rather than not see in water. So this is probably why the eyes of humans and a lot of animals are actually tuned to this kind of wavelength range. Okay, anyway, so this is the visible light range. So here it's very transparent. Here is not very transparent. So actually, in terms of the microwave, you actually want the microwave to be kind of fairly transparent to it, because transparent means that you've got this piece of food here, microwaves are going to go actually through it and not just be like absorbed on the surface. And so basically what you don't want is this situation where it's completely burnt on the outside and frozen on the inside. So this is not some meme which I found, but that would be basically what would happen if you use the wrong frequency microwave. Okay, so you can see around about 12 centimeters, which is the thing that's actually used. It's actually getting to be fairly transparent. Over here, the absorption coefficient is still pretty high, which would mean that actually it wouldn't be able to penetrate food very well. Okay, so so that kind of explains why, so I think people just found this frequency just through trial and error. They just, microwaved a bunch of stuff and then changed the frequency and then figured out what what actually works best. So it's kind of a you know, experimentally found kind of frequency. So how does microwave actually heat up stuff? So basically, it's again a little bit like the whole antenna kind of thing. So if you go back to the whole idea of how an antenna works, you have electromagnetic radiation coming in, and eventually this is going to move some charges around. So basically, any kind of food that we're talking about generally always contains water. There's almost every kind of food that we eat contains water, except for maybe some super dry stuff. So clearly, those things don't really work very well in a microwave, but almost everything has water in it. Okay, so basically what we're trying to do is heat up the water. And microwaves, basically what they do is they actually kind of rotate these water molecules. And this actually works because, so just like in an antenna where if you have electromagnetic radiation, it's going to start to move the charges inside the antenna around. For the kind of frequencies that the microwave radiation uses, basically what this does is to move the charges of the water molecule. And because water molecules are actually polar molecules, so actually the oxygen is negatively charged and the hydrogen is positively charged. So you have actually a little kind of dipole, which is effectively like a plus and a minus charge. What the microwave radiation actually does is to kind of, just like in the antenna where the plus and the minus charges sort of start to go back and forth, the microwaves also will start to try to move these plus and minus charges, and basically that means actually so if you've got a oscillating electric field, then basically all these water molecules will start to kind of like rotate because of the applied microwave. So and certainly, basically the temperature of something is something got to do with how much energy the atoms that make up the object actually have. So when you apply your microwave, just like in this little cartoon here, the microwave comes in and then, your water molecules all start spinning. Okay, and but you kind of don't want them just to be spinning. You want actually them to be all jiggling about. If you're talking about something that's hot, this kind of animation is, more like what it's supposed to look like. So essentially, what really is going to happen is actually the water molecules are going to be rotating, and then it kind of like bumps into like another molecule, and then that will sort of go flying, and then that's also going to be rotating. And then so actually the rotation is just sort of starting off this process of it actually all randomly bumping into each other. Okay. So overall, eventually this actually kind of causes heating in a more kind of conventional way. So it's not as if like each of the atoms are just like rotating a lot now. What actually happens is that, the water is a liquid, of course, so that the molecules actually roam around, rotate, bump around, and then, eventually it's like this chaotic, kind of jumble of atoms moving around. Okay, so again, this is, what I was planning to do was to do a bunch of experiments. Now, I'm not sure if I would have been able to pull this off because I'd have to source some dry ice, but what do you guys what do you guys think would happen if you microwave dry ice?
It will not heat up?
Yes. Exactly. Yeah, you might actually expect that. I mean, dry ice. Like just when you heat it up even a little bit, there's like smoke everywhere and all this kind of stuff. But yes, exactly. Actually, because the microwave is tuned very much to heating water, and what's dry ice made of? Anyone?
Carbon dioxide.
Yeah, exactly. Yes, because it's actually not really made of water; it's made of carbon dioxide. So this actually means that it's not particularly tuned towards actually heating up carbon dioxide. I think you maybe need a different kind of frequency. So there is a video of this. So let's just see this experiment kind of action. So.
Hello my friends, how y'all doing? Have you ever wondered what happens if you put dry ice into the microwave? Let's check it out. I have half a kilogram of dry ice in here. Check this out. Pretty much nothing happened. Like I said before, the dry ice is virtually indestructible. It's been 5 minutes in the microwave and nothing happened. That's crazy. The microwave was making weird noises, but nothing happened.
So yes, so absolutely correct. Actually, not much happens. So it's not like microwave is actually something that always heats up anything. It's yeah, well, like I said, very much dependent upon the kind of material. Okay, so similar. Oh, sorry, I'm not sharing the right thing. Go back. So slightly similar kind of idea. Okay, not exactly the same. Goes for also microwaving ice. Okay, so just water ice, so not dry ice, but just regular ice. So actually, also microwaving regular ice, it's not really very efficient. It's a lot better than the dry ice case, but actually it's still not really great. And the reason why is that what we really want to happen when you microwave something is actually the atoms to rotate, but also to kind of bump into each other. And because actually in an ice crystal, what you really have is kind of like it's like kind of loose ionic bonds. If you've ever done chemistry, ionic bonds are like when you have like a plus and a minus charge, and then they're sort of attracted to each other, and then you have this lattice of atoms or molecules that kind of form the crystal. And so, because actually the water molecules are not very free to move around, they have to actually fight against basically being locked into place by basically these mutual ionic bonds. The rotation doesn't happen very easily, and also they're kind of locked in place, so they don't really have much opportunity to sort of bump into some other neighboring atoms and then give them the kinetic energy. And so actually what you have when you microwave ice is what you're really doing is, so some of the ice actually melts, and there is some water in it, and then so basically what will happen is that the microwave will heat up that water very well, but actually not heat up the ice very well. So this explains one of the things which was over here. It says things you should never really put in a microwave: frozen meat, not because anything bad happens. I'm sure you've probably all tried to defrost meat in a microwave before, but I mean, you shouldn't try to sort of like cook it in the microwave, because actually the ice in the meat will not be very efficiently heated up, and basically you wouldn't really be able to kind of defrost or even cook the meat very well. Okay. All right. Another question is, so why do microwaves have these turntables? So some of them do have these turntables, some of them don't. Can anybody tell me why microwaves have these turntables? No idea? Well, I mean, it's actually a little bit more obvious for this one. This is almost not really a physics question. It's more of a cooking question.
Evenly heat up the object.
Yeah, exactly. So it evenly doesn't, without the turntable, it doesn't evenly, heat up the object. And, I think like my microwave at home, it doesn't actually have a turntable. And so you sort of notice it a little bit more, you have something where it's like really hot on like one part of it and like not hot at all on another part. So, why does this happen? It's basically because microwaves are actually produced in the oven, but because it's basically like a box, there are standing waves that happen that basically get generated within the microwave, and well, as we said, that this means there are hot and cold spots. But what are these standing waves? Actually, sorry, I think I wanted to do this one. So you might be familiar from this from the lab. Did you guys do an experiment like this? Standing waves is one of the lab experiments.
No, I think.
No. Okay. No. Okay. So, all right. But well, okay. You might have seen this somewhere before, but if you have a piece of string here, and basically this is one of the sort of classic first year physics experiments that everybody does in the lab, but you have a piece of string and then you have something that like makes it vibrate, and depending upon like the frequency, you get like these kind of waves that kind of form, and you can either get like like one big wave like this, or like two or three or something like this. And then so there are particular frequencies that are actually kind of resonant with this box. This is actually also how you get various different tones in musical instruments. So if you have like I don't know, trumpet or trombone or something like this, then you get these standing waves within the instrument. Okay, so basically same kind of thing is actually happening in microwave. You have this kind of standing wave pattern, and actually it really means that the wave is it's not like a random frequency, but it's actually a very coherent wave that is actually being produced. And this is the origin of the hot and cold spots, so basically standing waves. And another feature of a microwave, you probably often see this type of wire mesh on the window of the microwave. You might have wondered why is it always this wire mesh? Why do all the microwave manufacturers always, looks like a design thing, right? It's actually not a design thing. It's actually basically to block the microwave frequency. So you need this kind of metal mesh in order so that the microwave doesn't come outside, and you definitely don't want microwaves coming outside of the microwave oven, because obviously if it can cook your food and potentially heat it up to very high temperatures, it could also cook your hand or anything that happens to be very close. So you definitely want to block microwaves that are actually produced within the oven, and you want them to basically stay within the oven. Okay, and then so if you have just a regular piece of glass, then these microwaves might just come outside and then accidentally cook your hand, or maybe your face. It's like you're trying to look in the microwave. So this wire mesh there is there to block it. And so the reason why it's in this mesh kind of pattern is that the wavelength of microwaves are about 12 centimeters. And I don't know if any of you have studied this, what happens when you have a wave that, for example, if you've got waves like water waves that are coming towards like two slits. Has anybody of you done this like double slit experiment, diffraction or interference? Has Has any of you done this?
Is one of those simulations, online simulations for the lab session.
Yeah. Okay. Good. Yes. So when you want to see like this kind of interference pattern, and then there's some kind of interference pattern that you get on the side if you guys have seen it. So this works very well if like basically like for example the distance between these slits or basically if the wavelength of the waves here are like quite similar to this, okay, and likewise if you've got like a single slit diffraction experiment, then what you want here is actually that the wavelength is about the same size as the diameter of this slit here, okay. So the smaller the slit is, the more kind of round this comes in. If this slit is very wide, there's not much kind of interference. And so why they make these slits, like the holes in this mesh are maybe about 1 millimeter or something like that. Basically, by making it really small like that, it makes it basically equivalent to just having like a metal sheet there. And basically blocks most of the microwaves that are coming through there. You obviously want holes in it so you can actually still see what's going on inside, right? So you want that window there so you can kind of see what's happening. But having the mesh will actually block the microwaves quite efficiently. Okay. Yeah. Okay. All right. Maybe I'll skip that. Okay. So let's have a look at this video. I've got a little bit of time left, and basically this will show you, what kind of thing will happen if you are actually put some metal inside the microwave. So let's just quick look here. This guy. Have I got the right? Another ad. Hold on. Let me try and get rid of the ad first.
Hi, is it possible to put metal in a microwave oven? Let's put this spoon for 30 seconds and see what happens. Okay. It's a little bit hot, not too awful though. So I guess there has been some high amounts of current running through the metal to make it still touchably warm. So not a lot of power consumption. But now, what if I put 2 spoons side by side in there? Here we go. Still nothing, eh? Well, ouch, they are hot, but nothing terrible happened. I mean, the food gets hot in there too, so what's the big deal? Well, let's raise them a little bit on this empty cardboard box and see if that makes a difference. Still nothing. I bet these are pretty hot now. Oh, even the cardboard box is hot. Ow. Let's place them pretty close without touching. Ready? No problem. So I guess it's okay to put metal in the microwave. No! We must be missing something. Wasn't putting metal in the microwave supposed to be dangerous? Let's put them in this glass at an angle and maybe that makes a difference. No touching. There is only this much space between the spoons and there is still no arcing. Who said that it was dangerous to put them in there? So the question is, under what condition it gets dangerous to put metal in the microwave? I have seen these metal stands for microwave ovens that they put food over to warm it up.
So I guess it is okay under some conditions to put metal in the microwave, but what? For example, it should be fine to place a flat piece of metal in the oven without a problem. See? Metal in general reflects most of the electromagnetic wave in there, but obviously it's getting warm, so it must be absorbing some of it. Yeah, it's a little warm, not too bad actually. I mean, the body of the oven is made of metal, so it's all reflective and shouldn't be a problem. And I assume this also acts as a very good reflector. I wonder what happens if I place a spoon with a distance on top of this in the oven. Let's give it a try. Yeah. Let's bring the spoon even closer to the aluminum sheet. Still no arcing though, but I bet they're all getting warm. Ow, yeah, they are pretty hot. Let's try again. I put the spoon directly on top of the aluminum foil. I bet nothing happens again. It was supposed to be dangerous. I'm going to put these spoons vertical and parallel to each other like this in the oven and see what happens. There we are. Was expecting some good arcing. Nothing. Ooh, smoke. What's going on? Oh, no, no, no. It's gonna set my alarm. My clamp melted in there. So something is getting warm, damn it. Well, if I remember correctly, if you put two aluminum foils like this close to each other in the oven, it should arc. Well, let's see. Oh, jeez. Finally, there we are. It melted, but apparently not because it arced to this one, because this one is not melted. So what's going on? Let's just put one of them in there and see what happens. Why did this one melt then? Try again in a different location. Ooh. Where is it arcing to? I think I see what might be going on. It's just jumping from the very sharp edges. Maybe that's why.
Okay. Unfortunately, this is around about the time we've got to go. So maybe we can pick this up in the next lecture. But basically, what you're seeing here, well, you know, we're kind of looking at this guy experimentally find, you know, basically what happens with metal. But actually, you know, almost in every case, you know, there's actually not much that happens. Basically, the only way that you can really see anything happen is if you actually put aluminium foil. And well, we'll talk a little bit more about why that is maybe next lecture. Okay, so maybe we'll leave it there, and I'll see you guys on Wednesday.
Professor, you what about the final exam? What is the arrangement?
So we will send you a take-home exam, and you'll have 24 hours to do